Assalamu alaikum dear students, welcome to my channel. In today's lecture we are going to prove Cantor's theorem for set theory. Another theorem that is related to set theory will also be proved in today's lecture. Okay, so let's start with the preliminaries that we need in proving these two theorems. Okay, so first of all I would like you to recall the definition of a 1-1 function. Okay, so 1-1 function is a function in which you have a unique input for every output. Okay, if this is the case, then you will say that the function is 1-1. So if you look at the bookish definition, it says that a function f from a to b is said to be a 1-1 function if for all a b belong to a, where a is not equal to b, we have f of a not equal to f of b. Yani for different entries, for different inputs, we will have different outputs. We can't have the same output for two different inputs. So this is the definition of 1-1 function. Furthermore, if we move on, we have the statement of a famous density theorem from real analysis. We are going to use this in our proof. Okay, so what does it say? It says that between any two reals there is a rational. Okay, if you have any two real numbers which are of course different, so there will exist a rational between them. Actually there are infinitely many rationals between them, but we prove existence by saying that there exists one rational between them. Okay, so and I have proved this in one of my videos which is in the playlist of real analysis. I have put the link in the description below. You can watch that from here. Okay, and the next definition that we are going to use is the definition of the characteristic or indicator function. Okay, so what is this function? It is a function from a given set A to this set, which includes only two elements, 0 and 1, as you can see, and this function is defined as follows. When the function applies on an input from the set A, it will give you answer as 1 or as 0 depending on these two conditions. Okay, so here you can see another set B which is affecting our output. Okay, so what is this B? First of all, this B is a subset of the given set A. Okay, so actually this functions tells you that whether a given number from the original set A, a given element from the original set A belongs to this set B or not. If the given number, given element from A belongs to this subset B of A, you will have the answer 1. Okay, and if the element that you have been given does not belong to this subset B of A, then you will have the output 0. Okay, this is known as characteristic or indicator function. Okay, if you have any confusion, you can pause the video and rewind this. Okay, then you will find it very easy to understand. And another thing that is must to mention here is the class of all characteristic functions or indicator functions of the set of positive integers. Okay, set of positive integers have infinitely many subsets. As you can see that this set itself is an infinite set. Okay, and if you think about it for a moment, you will realize that the cardinality of set of positive integers is alpha naught. Okay, you can see that from your previous lectures. I have told that the cardinality of set of positive integers is alpha naught. Okay, and from our theory for finite sets, we know that the number of elements in the power set of a set, or you can say the number of possible subsets of a set, is equal to the 2 to the power the cardinality of that set. And if I am looking for the number of subsets of set of positive integers, how many subsets will be there? It will be 2 to the power alpha naught. Why? Because alpha naught is the cardinality, is the number of element in the set of positive integers. Okay, so we will have 2 to the power alpha naught elements or subsets of set of positive integers. Okay, so as you can see from this definition, the indicator or characteristic function is basically related to the subsets of that given set. Okay, so how many indicator functions or characteristic functions can be related to a given set? It's very obvious. It is the number of subsets of that set. Okay, so if A has 3 subsets, for example, if this A has 3 subsets, then how many characteristic or indicator functions will be related to this set? It will be 3. Okay, I hope so this will be clear, and if it is not clear, then you can rewind this video and then see this again. Okay, so finally from here we say that the cardinality of this class of functions over C positive, I mean set of positive integers, will be 2 to the power n naught, because this class of functions is actually containing all possible characteristic or indicator functions defined on this set. And I have told you that this is equal to the number of possible subsets of that set. We have Z positive, okay, and the number of possible subsets of Z positive is from here 2 to the power alpha naught. So this set has cardinality 2 to the power alpha naught. So students, here we have the statement of Cantor's theorem. It says that for any set A, we have the cardinality of A less than the cardinality of its power set. Okay, and to start its proof, we will consider a mapping. Okay, and I name this mapping as G from the set A to its power set, and it is defined as G of A is equal to the singleton set A. It's a well-defined mapping, you can easily check it. Okay, and now I'm going to show that this map is 1 1. By the way, it's very obvious from here. If you have a set A which, for example, contains 2 elements, let me give you an example, a very particular example, so that you can understand it well. Okay, for example, we have a set A which contains 2 elements 1 and 2, for example. Okay, so its power set will contain following subsets: the empty subset, the singleton 1, the singleton 2, and then a set which contains all the possible elements of that set. Okay, so these are possible subsets of this set A. From here it is clear that if you take this set A over here and its power set over here, and you define mapping like this, so this one will be a 1 1 function. Why? Because here input will be unique with respect to output. It is not possible, it is never ever possible that you will have this as output of both 1 and 2. That is not possible. Okay, so this is a 1 1 function. It's very obvious from here. So I can say this very safely, that the mapping G is 1 1 mapping. Okay, it's a 1 to 1 map, 1 to 1 function, whatever you call it. So if you are saying that this map is a 1 1 map between these two sets, what does it mean? From our literature we know that if you can perform a 1 1 mapping between two sets, then the input set will be, the cardinality of input set will be less than or equal to the cardinality of output set. So from here we conclude that the cardinality of A is less than or equal to the cardinality of the output set, or you can say codomain. Okay, this is our result from set theory. We have already studied it, and you can see that from your book. And for this video I am using the Sham outline series of elementary set theory. Okay, so you can see that from there. It's a proof, it has been already proved in our previous classes. You can see that from there. So what we have proved, that the cardinality of this set A is less than or equal to the cardinality of its power set P of A. So what is left for us to prove? The only thing that is left for us to prove is to prove that the case over here, the equality case, is not the truth. Okay, that is, we need to prove that this case is not possible. The cardinality of the set A and the cardinality of its power set are not equal. They are never ever equal. We have to prove this. Okay, and to prove this, we are going to adopt a very new strategy. We are going to introduce a new kind of elements. Okay, and we call these elements to be bad elements. It's a very interesting name, by the way. We call these elements to be bad elements. And what are these bad elements? Bad elements are the elements of this set A which does not belong to their image set. Okay, an element of A which does not belongs to its image set, such element will be regarded as a bad element. Okay, let me repeat this. Any element of this set A will be regarded as a bad element if when you apply the function g, on it, and the resultant set does not include that element A, then you will call this element A to be a bad element. Okay, and now if we take all the bad elements in this set A and we make it another set, okay, and this set will be called as B. Okay, so our new set B is containing all those elements X from A which are not a part of their image. Okay, and again I'm using the term F. I should replace it with G. I hope so this is clear. If it is not clear, you can rewind the video and see this concept again. Okay, so this set B is containing all the elements which are regarded as bad element by our definition, and the definition is written over here. Any element of A which is not a part of its image set, such an element will be regarded as a bad element. So this set B is containing all bad elements of the set A. So if you are saying that B is containing all bad elements of this set A, it's quite obvious that this set B is a subset of A. This set B is a subset of A. Okay, now we are going to introduce another mapping. Okay, and this mapping, this time we are saying that this mapping is F, and it is again from A to P of A, defined as usual. And we are saying that what we need to prove here, we are actually proving that the cardinality of A and the cardinality of P of A are not equal. But we suppose for a moment on contrary that this is not the case. The cardinality of A and the cardinality of its power set are equal. Though we need to prove that they are not equal, but we are supposing on contrary that they are equal. Okay, so if you are saying that the cardinality of A is equal to the cardinality of B, then what does it mean? It means that you can define a bijection between these two sets, and this is that bijection that we are talking about. Okay, now let me take you back. We were here. We have concluded that this B is a subset of A. Okay, so if this B is a subset of A, and we know that all possible subsets of A are actually lying here in this set, so can we say that this B belongs to the power set of A? Of course we can, because it contains all possible subsets of A. Okay, Now if you are saying that B belongs to this set P of A, and we also know that this mapping is a bijective mapping, so every image has a pre-image. Okay, that is the condition of bijection, that every element of this set must be an output of this set element. Okay, any element of this set. Okay, so from here we say that there exists an element B of the set A for which we have this capital B as our image. Okay, let me repeat this. Since we have concluded that this B is a subset of A and it belongs to this power set of A, so there must exist an element of A whose image will be this set B. Okay, so from here we have concluded that f of B is equal to B. Now two cases arises from here about this element B of A. As you can see, we have actually partitioned the set A into two parts. Either it contains elements which are good elements or it contains elements which are bad elements. Okay, I suppose that you recall the definition, you have not forgotten it so far. Okay, if you have forgotten, you can rewind the video and go there, and then you can recall that definition. So either the element in A is a bad element or it is a good element. Okay, so we are going to consider both cases. So first of all, we suppose that this element B, it's a good element. It's a good element. Though I have not defined it exclusively, but it is opposite of bad element. Okay, bad element was an element which is not a part of its image set. So good element will be an element which will be a part of its image set. Okay, so if you are saying that this B is a good element, then it means that this B will belong to its image set. Okay, and you know that from here that f of B is equal to B. So actually you have proved somehow that a good element is belonging to a set which contains only bad elements. Now is this possible? Of course it is not. So here we have a contradiction. If you take B to be a good element, you will face a contradiction. Okay, and now we are going to take this B as a bad element and let's see what happens. Well, in this case, if you are saying that this B is a bad element, then it should not be a part of its image, and we know that f of B is equal to B. So actually we are saying that this B is not belonging to the set capital B. What was this element B? It was a bad element. What was this set B? It was a set which was consisting of all bad elements. So how is it possible then this B does not belong to the capital set B? So this is a contradiction. Okay, again we are going to have a contradiction. Okay, which finally helps us to realize that our supposition, we were supposing that the cardinality of A and the cardinality of its power set are equal. This was our supposition before going on here. Okay, so these two contradictions helps us to understand that our supposition was actually wrong, and the cardinality of A and the cardinality of P of A are not equal. Okay, so in the start we have proved that the cardinality of A is either less or equal to the cardinality of its power set, and from here we have eradicated the possibility of equality. So this helps us to finally conclude that the cardinality of A is less than the cardinality of its power set. Okay, and this was the statement of Cantor's theorem. So this finally completes the proof. So students, here we have the statement of the second theorem that we are going to prove today. And it says that the cardinality of a set having power of the continuum. What does it mean? It is a set which is not countable and is not a finite set, okay, is the same as the cardinality of the power set of a denumerable set, okay. So first of all, I would like you to recall this term, denumerable sets. What are denumerable sets? Denumerable sets are the sets which are infinite but are countable, just like the set of positive integers, okay, the set of rationals and so on, okay. So we are saying that a set which is infinite and is uncountable, its cardinality will be same as the power set of a denumerable set, okay. Their cardinality will be same. This is what we need to prove. And you know very well that if a set has the power of the continuum, its cardinality is denoted by C, okay. And you know very well that the denumerable set has the cardinality alpha naught, and if you are taking the cardinality of its power set, that will be 2 to the power alpha naught, okay. So now we are going to prove this statement, and first of all we will consider two sets, okay, and those two sets are very well known to you people. One of them is the set of reals whose cardinality is, you know very well, it has the power of the continuum, so its cardinality is C. And the other set is the power set of rationals, and you know very well its cardinality will be 2 to the power alpha naught. Why? Because it's a denumerable set, and the cardinality of its power set will be obviously 2 to the power alpha naught. So I'm going to introduce a mapping between these two sets, okay, and the mapping is, I call it F. It's a mapping from the set of reals to the set of rationals, the power set of rational, P of Q, and it is defined as if you take any real number A and apply F on it, you will have a subset of rational number. And what will be that set of rational number? It will contain all those X which are rationals and are less than the input A, okay. So basically this mapping will give you all those rationals which are less than the entered real number, okay. So this is the definition of our function. And now I would like you to recall the definition, the statement of the theorem, the density theorem actually, which I have discussed in our preliminaries. If you have forgotten, you can go back, you can rewind the video and go there and you can have a look at that. If you are interested in its proof, you can see that video in the watch list real analysis. I have proved it there as well, okay, and I have given the link of that in the description below. You can find it, okay. So you have defined this mapping to be like this, okay. Now I'm going to use the density theorem. How? So if you take any two real numbers from this set A and B, I call those two real numbers to be A and B. So by density theorem, there will exist a rational between them. A is less than R is less than B, where this R is actually representing any rational number, okay. Now by definition, can we say from here that R will belong to F of B? How? F of B will give us a set of rationals containing all those rationals which are less than B. And as you can see from here that R is a rational and is less than B, so it will also be included in that set F of B. I hope so it will be clear, okay. But at the same time, this R will not be a part of F of A. And why am I saying so? Because F of A will give you a subset of rationals which contain all those rationals which are less than this A. And as you can see that A is less than R, so anything which is less than A will not include this R. Okay, it's a very simple understandable concept for you people. Okay, so you have shown that a number R is belonging to f of b but is not belonging to f of a, which finally helps us to understand that f of a and f of b, these two are not equal. And if they are not equal, then this implies that the function f is 1, 1. It's a one-to-one function. And if this is a one-to-one function, I have told you before that in that case, the cardinality of the input set will be less than or equal to the cardinality of the output set, or you can call it the codomain. Okay, so from here we conclude that the cardinality of R, which I have mentioned as C, this C is less than or equal to the cardinality of this set P of Q, and I have told you that its cardinality is 2 to the power alpha naught. So we have 2 to the power alpha naught. And I label this inequality as inequality number 1 because I am going to use this. So students, now we are going to introduce another map, and this time I call it the capital F, and it is a map which is being introduced from the set C of Z positive to another set which is a closed interval 0, 1. Okay. And let me tell you first of all that the cardinality of this set is, as I have already mentioned in the preliminaries, that its cardinality is 2 to the power alpha naught, and the cardinality of this interval, which has the power of the continuum, its cardinality is C. Okay, so what we need to prove here is that this 2 to the power alpha naught is less than or equal to C, and then we will use the fact that if A is less than equal to B and B is also less than equal to A, then A and B are equal. Okay, so we will say that if C is less than equal to 2 to the power alpha naught, and if 2 to the power alpha naught is less than equal to C, this finally means that these two are actually equal. Okay, and for that I am going to use this function over here. Okay, so let me introduce the mapping. How is it defined? It is defined as that when f applies on any characteristic function, because this is the class of characteristic functions defined on the set of positive integers. I have mentioned it in the preliminaries. Okay, if you have any confusion, you may rewind this video, go there, watch those videos, watch those procedures again, and then you will come here and you will find it very easy to understand. So it is a class of all characteristic functions defined on this set of positive integers. So if this f applies on any of that function, suppose we have function fa, we will have the input just like this: 0 point fa at 1, fa at 2, fa at 3, and so on. So this will give us a number. If you apply the mapping capital F on a characteristic function of set of positive integer, this will give us a number in the decimal form 0 point something. Okay, and that something is actually depending on the values here. So fa with respect to 1 will give us the value 0 or 1. If the element, this element 1, is belonging to the subset A of positive integers, you will have its answer as 1. And if this 1 is not an element of this subset A of positive integers, then you will have 0. Okay, so it's a number of the form, for example 0.1110001010110 and so on. Okay, it's a kind of that number. Okay, so this is how we have defined, and it's a well defined mapping. You can check it very easily. Okay, now if you take any two characteristic functions, let's say one of them is fa and the other is fb, any two characteristic functions from this class of characteristic functions defined over set of positive integers, and we say that we suppose that this fa is not equal to fb. So if you are saying that fa is not equal to fb, in that case we can easily say that 0.fa at 1, fa at 2, fa at 3 will not be equal to, and this is going on and on, this will not be equal to 0.fb at 1, fb at 2, fb at 3 and so on. These two numbers will not be equal. Why? Because we have said that fa is not equal to fb. They are not going to give you the same output. So if they are not going to give you the same output, how can we say that these two numbers will be equal? Okay, so these two numbers will not be equal. And if you look closely, this number is actually the image of f at fa, and this one is the image of capital F at fb. So finally we have shown that capital F when applied on fa and the same capital F when applied on fb will give you different answers if this fa and this fb are not the same. They are not equal. Okay, and what does it mean? It means that the function that we defined here, this function, is actually 1, this function is actually a 1-to-1 function. And if this function is 1-to-1, what does that mean? It means the cardinality of this input set will be less than or equal to the cardinality of the output set. And as I have told you earlier that the cardinality of this input set here is 2 to the power alpha naught, and the cardinality of our output set is c, being the power of the continuum. Okay, so we have this relation, and I call this as inequality number 2. Okay, so in the first part of the theorem we have proved that c is less than equal to 2 to the power alpha naught, and now we have proved that 2 to the power alpha naught is less than or equal to c. So we have studied a property of the real numbers, that if a and b are any two reals such that a is less than equal to b and b is less than equal to a, then this implies that actually a and b are equal. So from here, the inequality number 2 and the inequality number 1, we finally conclude that c is equal to 2 to the power alpha naught. And you can see from here, this was what we needed to prove. Okay, so this completes the proof. Please share and like this video, subscribe my channel, hit the bell icon so that you don't miss any update in the future. Thank you so much. It's a proven fact that generosity makes you a happy person. So please be generous, subscribe our channel and hit the bell icon. Thank you.